This is part 3 of the video lecture for Math 140 for Tuesday, May 5th. And the topic today, again, is ellipses. In this third part of the video, I want to talk about the definition of an ellipse, derive what's called the foci formula, and talk about the eccentricity of an ellipse, and then talk about a couple important applications. We talked about the equation of an ellipse. We basically said, kind of roughly speaking, an ellipse is a stretched out circle. But what really is the precise definition of an ellipse? Well, it turns out an ellipse, besides having a center, an ellipse has two foci. That's the plural of focus. So an ellipse has two foci. Okay, and the definition of an ellipse is it's the set of all points such that the sum of the distances from the two foci to those points is a constant. Let me say that again. It's the set of all points such that the sum of the distances from the two foci to those points is a constant. Okay. So as I move this point around, this distance will change and this distance will change, but the sum of these two distances remains the same. And we can express that in an equation which says f1p, which is the distance from one of the foci to this point, plus the distance between the other focus to that point. The sum of those two distances is a constant k. We'll call it k. Okay, and actually there's a really fun, easy way to draw an ellipse that I won't do. I've done this demo before, but I won't do it here. But what you can do is you can actually take a piece of cardboard and put two tacks on the cardboard which represent your foci. And then you can take a piece of string of a fixed length. Okay, and you can tie that string to the two foci, and then take a pencil, and then as you move around, that length of string stays the same. These two distances change, but the total distance stays the same. And you can actually trace out you can make an ellipse just by using those simple tools. So that's kind of cool. Okay, what I also want to do here is I want to derive what's called the foci formula, and let's imagine we have an ellipse here. It's a horizontally oriented ellipse. Okay, the distance from the center, the horizontal distance from the center to the ellipse is A. The vertical distance from the center to the ellipse is B. Okay. In other words, and by the way, A is, if you've noticed by now, A is the quote semi-major axis of this ellipse. 2A is the major axis. A is the semi-major axis. 2B is the minor axis of this ellipse, and B is the semi-minor axis. Okay, and then I can consider 4 points on the ellipse. This horizontal point, this will be a distance A from the center, so the coordinates of this point are A, 0. This is 0, B because it's B units above the center, and so on. By the way, you won't be responsible for deriving this formula, so don't worry about having to reproduce that in the test, although it might be extra credit. But I just wanted to show you how to derive this formula. So what I'm going to do is label various distances here. This distance right here is B. I'm considering now a point. So I'm considering the point, this point in particular, 0, B, the point that's directly above the center. Excuse me, this is B. Okay. The distance between the center and the focus I will call C. Okay, that's going to be equal to C. So this distance is C as well. Okay, and this point is minus C, 0. This point is C, 0. Okay. And then what I want to do is I want to figure out what this distance is right here. Okay, this distance D, I'm going to figure it out. Well, we have two identical right triangles here, and so I can use the Pythagorean theorem. And the distance D is equal to the square root of B squared plus C squared. Okay. And this distance D is equal to that as well. But we also know for an ellipse, the sum of the distances from the two foci to any point in the ellipse is a constant k. So what's the sum of these two distances? Well, the sum is D plus D. We've got D plus D. That's the sum of the two distances. That's equal to 2D. That's equal to 2 times the square root of B squared plus C squared. And as we said, this defines an ellipse, and we're going to call this distance, whatever this distance is, I don't know what it is, I'm going to call it K. it's this constant k. No matter where I go on the ellipse, the distances from the two foci to any point is a constant k. So we'll just call it k. Okay, now I want to consider, so this is point, I'm considering point 0b here, and this is what I found. Now let's consider the point a comma 0. Let's move to this point along the ellipse. Okay, and let's figure out some distances here. Now, what is this distance? Let me move this down a bit here. C comma 0 up there. What is this distance right here? Okay, this distance right here, this is A, and this is C. So this distance right here is A minus C. Okay, so what is the distance between this point, this focus, F2? So the distance between F2 and the point A equals A comma 0, this distance is equal to A minus C. Okay. Now what's the distance from the other focus to this point? What is this total distance? Okay. So what is the distance from F1 to the point A comma 0? What is that distance equal to? Well, it's equal to this distance, it's equal to C, okay, plus this distance, okay, and what is this distance equal to? This is A, so this is A, so we get C plus A. Okay, but now for an ellipse, the sum of the distance, for any point in the ellipse, the sum of the distance from one focus and the distance from the other focus to any point is equal to this constant k. So we know that k is going to equal the sum of this distance and this distance. And so that's going to, k is going to equal a minus c plus c plus a. Okay. And these c's, we have a minus c and a plus c, so they go away. And this equals 2a. Okay, so considering this point, we know the distance between this point, the sum of the distances between this point and the two foci is 2a. Okay, I want to erase what's upstairs here. Again, you're not responsible for this derivation, but I thought it was kind of a cool thing to show you guys. So now I have two formulas. I have k equals 2 times square root of b squared plus c squared. And I have the formula k equals 2a. Well, this is now, we can use now the transitive property. When something equals something else, and that same something equals a third thing, these two things must be equal. So this leads me to this. 2a equals 2 square root of b squared minus plus c squared. Okay, and the 2's cancel here, and I get a squared, a equals the square root of b squared plus c squared. That's kind of a cool formula. If I square both sides, I get a squared equals b squared plus c squared. And now I'm going to solve for c squared. So I get c squared equals a squared minus b squared. And this is called the foci formula. I'm going to box it, make one small change here. This is called the foci formula. Or this is right here. This is the foci formula right here. Okay. In other words, this is a formula. If you know A and B, if you know the semi-major and semi-minor axes of your ellipse, you can calculate the distance of each focus from the center of the ellipse, which is C, by using this formula. Okay. One little caveat. Why did I put in the absolute value signs? Because in some cases B will be greater than A. You'll have a vertical ellipse, and you can't have C squared can't be negative. So we need to put on the absolute value signs. So this applies to both vertical and horizontal ellipses. But this is a pretty cool formula. C squared equals the absolute value of A squared minus B squared. Again, if you know the semi-major and semi-minor axes of an ellipse, you can calculate the distance of the foci from the center of the ellipse. Okay, I want to do one quick example problem and then just mention one application of ellipses. And actually, before I do the example problem, I want to mention one other aspect of ellipses. That's called eccentricity. Okay, eccentricity. Eccentricity is basically how stretched out an ellipse. I won't even write that down, but it's how stretched out an ellipse is. And eccentricities range. Eccentricity is represented with the symbol E. For ellipses, eccentricities range from 0 to up to 1. Okay, so for a circle, the eccentricity equals 0, and a circle could be represented like this. Or you could have a very stretched out ellipse. This is a very stretched out ellipse, and this has a large value of E. In fact, it's a value of E that's getting close to 1. So the more stretched out an ellipse is, the higher the eccentricity of that ellipse, and the closer E is equal to 1. Okay, a circle has 0 eccentricity. Now, eccentricity is defined as being equal to the ratio of C over A. That's defined as the eccentricity. And we also have our foci formula, which we found C squared. Let me just write this down here. C squared equals A squared minus B squared. You guys remember that formula? And I want to now do an example problem with this, involving this. And I know what I did is a little bit complicated, that derivation. The example is simple. I want to consider an ellipse that's equal to the equation of an ellipse. So let's consider this specific example. Okay, this is an ellipse. And the center, you guys can see the center is minus 1, 1. And we know that A is equal to 3 and B is equal to 2. What is the eccentricity of this ellipse? In other words, this ellipse is stretched out horizontally. How eccentric is it? How much stretched out is it? We can calculate C. Okay. C squared equals the absolute value of A squared. So 3 squared minus B squared, which is 2 squared. And this equals the absolute value of 9 minus 4, which equals the absolute value of 5, which is 5. Okay. And then if I take the square root to get C, the C equals the square root of 5, which is approximately, I think it's like 2.24 or something like that. So C is the square root of 5. In other words, for this ellipse, the distance from the center to each focus is a distance of square root of 5 from the center. What is the eccentricity here? The eccentricity is equal to C, which is square root of 5, divided by A, which is 3. Okay. And this comes out to 0.745. So this is a fairly eccentric circle, although not extremely eccentric. So this is an example problem where if we're given the equation of an ellipse in standard form, we can actually calculate the eccentricity using the foci formula. Okay, one last little tidbit for you guys to think about. A hugely important application of ellipses. You might wonder, what are the applications of ellipses? I'm a little bit biased because I studied astronomy in graduate school. It turns out the orbits of the planets and the asteroids and the comets follow elliptical patterns. At least comets that come back, that are not one-shot comets, but comets that repeat. And that was discovered by Kepler back in the early 1600s. He discovered that the orbits of the planets are elliptical in shape. And the planets have various eccentricities. So some planetary orbits are more stretched out or more eccentric, and some are less eccentric. I wanted to show you guys a table of the eccentricities of the planets. And you can see the orbital eccentricity on the left there. So, like for instance, Venus has an orbital eccentricity of 0.007. That means Venus is very close to having a circular orbit. Okay. Mercury and Pluto have higher eccentricities, 0.206, 0.248. So that means that they have more eccentric orbits. And what that really means is at times Mercury is a lot closer to the Sun, and at times Mercury is a lot farther away from the Sun. By the way, perihelion and aphelion, perihelion is the closest distance the planet comes to the Sun. This is listed in AU, which I mentioned to you guys before, but don't worry about it if you forgot what it means. It's not really part of this class too much. but then aphelion is the farthest distance from the sun. Earth doesn't have a very eccentric orbit. Earth has a fairly circular orbit, which means that, which is good for us, because if we had an eccentric orbit during certain times of the year, in addition to, I won't get into that, the seasons are caused by the tilt of the Earth, but if we had an eccentric orbit, that would, on top of the tilt of the Earth adding to the seasons, we also would have the effect of, when we're closer to the sun, we'd get hotter. And we don't, because we don't really change that much in our distance from the sun. So that's good news for the Earth, is the moral of that story. Anyway, that's a lot of astronomy stuff you guys don't need to necessarily know. I did want to show you guys a couple images. So this shows the orbits of the planets kind of looking top down, and there's the sun. Mercury has a highly eccentric orbit. Venus has a circular, fairly circular, Earth is fairly circular, and Mars has a more eccentric orbit. Like over here, Mars is farther away, and over here it's closer. So it's colder here than here, generally speaking. And then I wanted to show you guys, this is a view of the orbits of our entire solar system, including the outer planets. And you can see that Pluto, for instance, has an extremely eccentric orbit. And Pluto is essentially kind of a glorified comet. So anyway, the point of this is ellipses have really important applications to the planets, the orbits of the planets. And there's a wide variety in the eccentricities of the various planetary orbits. Okay, that concludes the video lecture. That's the last video lecture of the semester for me and for you guys. And I'll see you guys on Tuesday.